everybody. So, today we will be starting our first lecture on geometrical optics. Okay. So, what is the first thing that comes to your mind when we talk of well, geometrical optics? I suppose the first thing that comes to our mind is the passage of light through lenses, how so curved lenses, that's a convex lens or a concave lens, or maybe reflection from curved mirrors. So, but one has to realize that this is rather pretty old subject. This is rather a pretty old subject in physics. We've been doing things for hundreds of years. In fact, it's the use of these lenses and mirrors which had a huge role in the development of astronomy. For example, Galileo was the one who used just two lenses. He just used two lenses and then put it in a cylindrical tube, and he watched the moons of Jupiter, and he made certain astronomical observations. So, in a sense, well, this subject is it's one of the primary things which was responsible for advancements in astronomy, and not only in astronomy. I mean, not only in physics for that matter. I mean, if you think of the simple magnifying glass, okay, to look at small things. I mean, I bet the modern biology owes its origin to the observation of small things, right? So, the study of geometrical optics had rather far-reaching consequences, not only in the development of optics, but also in other branches of physics and also in other branches of science. Right. So, now that we know that it's an important thing to study, although it's an old subject, what is the area of applicability? Okay, so rather at what wavelength range should we apply geometrical optics? Now, why do I say that? Because at the back of your mind, you also have things like diffraction, interference, which have been explained so well with the electromagnetic waves. Okay, so what's the area of applicability here? For that, let's draw a simple diagram and define our area of applicability. So let's say we have a small slit or a small hole, okay, and we're going to put some source in front of that, okay, some source of light in front of that, right. Now, we put a screen a little distance away from this hole or from this slit. Now, what do we expect to observe? Well, I mean, we have a reasonably big hole here. So, we can draw these two lines. Okay, I will come to this point that we are drawing lines here, and then we observe the image of this slit or this hole on the screen. So, on this screen. Now, which is kept at a certain distance away from the slit. Okay. Now, if you observe, you have sharp boundaries for this image, okay, and you just observe only one image of this hole, then I am sure you are going to say that we are in this regime of geometrical optics. Now, why? I mean, look at the other extreme. I mean, if your hole is small enough, you will have if your hole is small enough, let's say, let me draw another picture. If your hole is small enough, you can have and then you put a source of light here. I call this some source. You're going to have alternate regions of light and dark regions. Okay. Now, that's diffraction. So, you have alternate regions of light and dark regions here. So, but the field of geometrical optics would not concern such a thing, would not be too concerned with this diffraction, okay, but would be talking of things in which when you have a slit, okay, the image of the slit is very well defined on the screen. Now, when does that happen? Well, that happens if the size of the slit that you have taken, okay, let us say the size of the slit is d. Now, that is much greater than the wavelength of light that you have used, okay. So, this is one important criterion for the application of geometrical optics, okay. And well, if it's not, if the slit dimension is some way it's very near or comparable to the dimensions of the wavelength, okay, you will, as I said, you will have to deal with things like diffraction, okay. So, this is one thing about the sizes. The second thing is a bit involved, but then it's another conceptual conceptual thing. It's that the light or the energy of the photon in this case, okay, should be lesser than the energy sensitivity of the instruments that you're using. So, it should not interact with the instruments, okay. So, basically you are not in the quantum region, quantum regime here. So, we are still in this classical regime, and we will be using what we call as these lines or these rays of light. Let me draw it once again. So, these are the rays of light by which you are going to get some sharp images on the screen, okay. Now, what are these rays of light? These rays of lights are nothing but infinitesimally thin. So, these will be using the rays of light, okay. So, and they are the infinitesimally thin beams of light, okay. Now, for that reason, geometrical optics is also called ray optics, okay. So, that is what we are going to study. We are going to study ray optics or geometrical optics here, okay. Now, let us do one more thing. Now that we know that we have we are going to deal with rays, okay. So, the next question to ask is what path do these rays take, okay. So, the question that we ask ourselves is what path does the ray of, let us say, the ray of light take, okay. Now, this was something which bothered many people, and quite early, and apparently people had lots of ideas. Well, they said that, oh, it will follow the least distance between 2 points. Well, if it's the same medium, that's fine. I mean, the least distance is fine, but that may not be the case in which you have in media of different refractive indices in between, okay. Now, I will come to that again. Now, apparently there is a principle which tells you what path the ray of light will take. Well, it is called Fermat's principle, or in its original form it is also called the principle of least time, okay. So, we will be talking of the Fermat's principle, or the principle of least time. Well, it simply states that well, the ray of light will follow that path from one point to another, in which I have point A and point B. Well, you can take whatever refractive index in between. Well, it will follow from point A to point B the path in which the time taken will be the least, will be the minimum one, Okay, so that was Fermat's principle in its original um, form. So that's what Fermat said, that light is going to travel from A and B, okay, and the path it's going to take is that for which the time is going to be minimum. So instead of this path or the other path, the one from A to B will be the one, the one the light will take, that the ray of light will take rather, will be the one in which the time taken is the least. Okay. Now, apparently the whole of geometrical optics can be derived in principle from this one simple concept. Okay. So, that is how important it is. Okay, well, in its this is the statement in its original form. It is the principle of least time. But I'll come a little later on some modifications. But let me just tell you 2 or 3 consequences of Fermat's principle. Okay, so let's just do 1 or 2 consequences of Fermat's principle. Consequences of Fermat's principle. Well, the first is that if from point A to point B, let us say light is travelling and it has taken the path of least time. So, point A to point B, suppose this is the path and this is the path of least time from point A to point B. Well, if I start from point B to point A, the light will actually take the same path back. Okay, so if it was the least time on one way, so it will be on the other way also, it will be the least time compared to other paths. Okay. Now, this is called the principle of reciprocity. Okay. So, it retraces its path back. So, this is the principle of reciprocity. Okay. Second thing is about well, I mean, what comes to my mind is, I mean, I started this talk on by talking of some lenses. Okay. So, let us draw a lens. Let us draw a simple convex lens. Okay. And on the axis, so light, let us say I have some point on the axis on the left hand side here. Okay. So, this is my convex lens, and then let us say the light from this point actually comes and then comes here, and then well, I have well, it comes on the other side. Okay. So, this is the object distance and this is the, let us say, the image distance, which I denote by V. Okay. Now, there are infinite paths of light. Let us just take 2 or 3 of them. There is one path which goes entirely through air. Okay. So, the one up at this point and then comes back here. There is one which goes partly through air, which is actually along the axis. Okay. And then there is one part which goes through the lens and then comes through and then comes and travels in air to reach the image point. Okay. Now, if you look at these 2 points, the length of these 2 points are different, the path lengths are different. Okay. The actual length from on the axis, that is the least compared to the length when it goes to the tip of the lens and then comes to the image point. Okay. Now, however, by the principle of least time, you can argue that the time taken by these 2 light rays, okay, but this one, the one in which I have drawn, the one goes to the tip and then comes to the image point, and the one in which it passes through the which is along the axis of the lens. Okay, both of them take the same time. Okay, otherwise you are not going to have an image on the other side. Okay. So, of course, I can also derive the simple laws of reflection and refraction using Fermat's principle. Okay. But before that, I wish to remind you once again about, well, maybe I haven't said this before, is about the statement of Fermat's principle. Well, now we don't say that the time taken is minimum. What we say is that the light will follow that path. So, from A and B. So, Fermat's principle, the way we say it now, Fermat's principle is that light will follow that path, will follow that path for which the time taken is actually an extremum, is actually an extremum compared to the nearby paths. Okay. Extremum compared to what? Compared to nearby paths. Now, when I say an extremum, I don't actually specify whether the time is actually minimum or maximum. It's an extremum. Okay. So, pictorially or diagrammatically, how do I write that? I mean, I have point A and point B. Okay, let's say point A and point B. Now, there are actually infinite number of paths which connect point A and point B. Okay. Now, what it tells, what Fermat's principle tells, is that light will follow that path for which the time taken is actually an extremum compared to these paths. Okay. Compared to, for example, it will follow the path in which I have shown by a solid line. Okay. As opposed to, and that will be an extremum path compared to, let us say, the ones which I show by the dashed lines. Okay. So, that is how we know Fermat's principle now. Now, this is actually a far-reaching consequence of the principle of least action, or again it is the Hamilton's principle in mechanics. Okay. Now, let's as I said, we can derive the laws of reflection and refraction from Fermat's principle. Let us see how we can do that. Okay. And so, that will give us some more confidence about the applicability of this theorem, of this principle rather. Okay. So, we want to check what happens during reflection. Let's draw a figure first. So, here we have a mirror, a plane mirror, let us say, and say we have a point A and a point B. So, let us say we have a point A and a point B. Now, the thing that we want to do here is that we want a ray of light to come and hit the mirror reflection and go to B. Now, which direction should it go? Well, common sense and what we have learnt in school is that, well, it should go in such a way that the angle of reflection should be equal to the angle of incidence, rather should be equal to the angle of reflection. Okay. Now, why is that? Because you see, from going from path from point A to B, via the mirror, I can actually have an infinite number of paths. Okay. Now, why should light choose the one in which the angle of incidence is equal to the angle of reflection? Let's find out using Fermat's principle. Okay. So let's draw a normal at the point of incidence. Okay, and consider that this point A is at an height h1 from the mirror, point B is at an height h2, and the distance on the mirror, the distance of the mirror is L, let us say, and let's also think that the distance at which the light strikes the mirror, that is x. Okay. So let me see, and have I drawn all the distances? Yes, I have taken the distance in the mirror, the distance where it hits the light hits the mirror is incident on the mirror. Okay, so I haven't drawn the angle of incidence. Let me call this I. Okay, and the other one here is the angle of reflection. Let me call this R. So, and this is the normal. Okay, so the one this dotted line is the normal, and I bet you're going to say that what will be this angle? This angle is also R, and this angle is I. Okay, and these are all right angle triangles. Okay, so let me I haven't labeled these points. The height of this is P. Let me call the point at which the light is incident as O, and let me also call this height, so B, this is Q. Okay, so PQ is L, PO is X some distance. Okay, and the height from the mirror is H1 here, and the height from the mirror height of the mirror of B is H2. Okay. Now the thing now the question that I am trying to address here is, I mean, light comes and hits the mirror at a distance x here. Well, it could have hit a little bit. I mean, if it hits at x, what happens to the angles? This is one thing. Or to put it in another way around, I mean, why should it hit only at x? It can hit at the other places and come to B. Okay. Now, which is the one, according to Fermat's principle, should be the path of the light here? Okay. So let's do this. What's the time it takes for light to go from, so time to travel, let's say, to travel the distance AOB, this distance AOB, let me call that time t, and the velocity of light in this medium. Okay, so let me say this medium itself is air, so velocity of light, let's say is c, or the speed of light is c. Okay, so what's the distance AO? Well, the distance AO is nothing but h1 square plus x squared by c. That's the time it takes to travel the distance AO, and the distance OB. So that will be square root of h2 square plus L minus x squared divided by c. Okay. Now, what do I do now? Now, I say that the time will be, I mean, compared to different paths, compared to its neighboring or nearby paths. So, this is going to be, I am going to have, this is going to be an extremum. Okay. So, that is what I have. So, I have, let me do this dt dx. So, this is equal to, what is dt dx? I am going to take n 1 by c here, that is the speed of light, that is a constant thing. I am going to differentiate the 1 in the square root. So, I will have a 2x at the top, and then if I differentiate this entire thing. So, I am going to have 2 times root over h1 squared plus x squared in the denominator. What about the one on the for the path OB? So, this is twice L minus x. So, I am going to differentiate this point h2 squared plus L minus x whole square and the square root of that. So, that is equal to twice of h2 squared plus L minus x whole square. Okay, so I have not taken the minus sign out, so because L minus x, okay, fine. I put a minus sign here, and then there was an 1 by c. Okay. So, when I say it is an extremum, I am going to put this equal to 0. So, which immediately tells me that x by root over h1 plus x square is equal to L1 minus x h2 squared plus L minus x root of that. So, what does this tell us? So, it tells us that if I want the time to be an extremum, okay, compared to all different paths light can travel. Now, if this is the path light should travel, okay, I better have x by, well, I should have put an h1 squared plus x square root over of that. That should be equal to L minus x h2 squared plus L minus x whole square and square root of that. Now, what does this mean? Let us look at this figure. Let us look at this triangle APO. Okay. Now, what is x? What is x divided by h1 squared by x1 square by x squared? Okay. So, let us look at triangle APO. Okay. Let us look at the figure triangle APO. Now, in triangle APO, what is the sine of the angle I? Well, it just happens to be x by the distance h1 square by x square. Okay. Now, compare that in triangle BOQ. What is the sine of the angle R? Okay. Now, these are what? So, sine of the angle R is L minus x divided by h2 square plus L minus x whole square, and take the square root of that in the denominator. So, which tells you immediately here that light will travel that path in which I am going to have just the in this same medium the sine of this angle I is equal to the sine of this angle R, or in other words, I need this angle I to be equal to the angle R, which is actually the familiar laws of the reflection that you have. Okay. So, well, to think of this as a mechanics problem is also quite interesting. Actually, if you set a problem like this, that I want to run from point A to, let us say, point B by touching some wall, okay, which is PQ. Now, which path should I take so that the time taken will be the least here? Okay. Well, actually, we will be taking that path for which the point at which you hit the wall, and then you draw a normal to that, then you find an angle, okay, that should be equal, and you still call that an angle of incidence, okay, should be equal to the angle that you make with the normal when you run away from the wall to reach point B. Okay. So, this again will actually follow from the principle of least action in mechanics. But right now we are doing geometrical optics, we are dealing with light, rays of light. So, and we have just now verified again the laws of reflection using Fermat's principle. Okay. Now, with this basic verification, how about doing it for the for diffraction? Okay. So, you can always say that, okay, fine, I have done this for a medium in which the refractive index is the same, right. So, the reflection is in this region in which you know, in the region AOB, that is in a region where the refractive index is the same. Okay. So, let us find out what it is going to be when you have two different media. Let us draw a figure once again. So, okay, so we have two media, okay, which is infinite on both sides, let us say. So, in one side the refractive index is N1 and on the other side the refractive index is N2. Okay. Now, you are at point A, let us say, and you wish to go to point some other point. Okay. Now, what is the point, what is the direction that you need to follow? Okay. In case you want to go to point A to point B. Is it this straight line? Well, I should draw the point B here. Is it the straight line? Well, that is the distance, that is the least distance. But then remember that the speed of light is different in these two media. Okay. So, the time taken is necessarily not the same if you go, it is definitely not the same when if you follow a straight line, or let us say you travel this much in one media and then the other here, or let us say you travel this much in medium 1 and then the one here. Well, it is more like you are on, let us say N1, so this is region 1, let us say this is land, and then N2, this is some water. Okay. You want to go from point A to point B. Okay. What do? Do you jump straight, you go straight into, do you go straight to the shore where water is and then swim all the way to B? Okay. Or do you want to minimize your swimming, because you know swimming, that's a bit tougher than just running on land, okay, because of resistance. So, do you maximize your path on land? Okay, let us say you come here and then you swim a little bit in the sea or in water. Let's not bring in sea or anything else, in water. So, which path should you take? Well, the problem is the same. So, let us redraw this figure once again and label it. So, let us say you need this to be the path, and this is how you wish to go. You are in point A and this is the point you are incident on the interface of both the media. So, I want to go to point B here. Let us say again I call this distance, let me call this distance well, this distance H1, this point as P, this point of contact within these two media where light comes and hits as O, and then B, and this to be H2, and then I call this PQ. So, this point is Q. Okay. Now, I again take this distance. So, this distance is fixed, this distance PQ, this distance PQ, this is, let us say, let us call that as L, distance L. Let me call PO, so that is X. Okay. So, that is variable. Where do I want to hit the surface here? Do I want to hit it here, 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 or here, so that the time it takes compared to all these paths to go from point A to point B is an extremum? Well, let us do that. So, definitely what is point OQ? So, this is L minus X. Okay. So, what is the time it takes to travel this distance AO? Okay. So, the time again to travel AOB, this distance AOB. So, this is let us say capital T. So, what is this distance by the way? So, this distance is AO in medium 1, okay, where I have the refractive index N1. Now, how is the velocity or the speed of light related with the refractive index? Well, if the speed of light in vacuum, in air in vacuum, let us say is c, and then I divide that in a medium where the speed of light is v, then the refractive index is n, right. So, what do I get? So, the velocity of light in a certain medium which has a refractive index n, is nothing but c by n, where c is the velocity of light or the speed of light in vacuum, and then n is the one in n is the refractive index here. Okay. So, the time it takes to go to do the distance AO, what is that? Well, let us find the distance. So, the distance is, so this is x, okay. So, this is nothing but again h1 squared by x squared. Now, you need to divide this by the velocity in medium 1 or the speed in medium 1, which is c by n1, because we are in medium 1. And now, we need to add again. So, this is the time it takes for light to traverse this distance AO. Okay. Now, what about this distance OB? Well, that is h2 squared plus L minus x whole squared divided by c by n2. Remember, the speed of light in medium 2, I call that velocity v2, and that is again dependent on the refractive index. The c is the speed of light in free space or the speed of light in vacuum, let us say. Right. Now, we need to take the extremum of this. So, which means we simply take dt dx is equal to 0. So, which tells us that well, c and n and all these things are constants here. So, we need to differentiate this entire expression with respect to x. So, what is that? So, that is n1 by c, and I am going to take a 2x upstairs, and so and then I differentiate that will be, so that is h1 squared plus x squared. So, differentiate 2 x squared, so I get a 2x here, and then again h1 squared by x squared. So, this half by this entire thing to the power 1 minus half. So, that is okay. So, the square root comes down, and then I have again n2 by c, the other one I get an, okay, so L minus 1, L minus x. So, I will have a minus sign here, and so I get a 2 of L minus x, okay, and again h2 squared plus L minus x whole squared. Okay. Okay. So, so what is the point? Well, what is the time light will take once it goes from point A to B and via this from one medium to another. So, we were calculating the time, and the time it takes to travel from A to AOB, we have calculated that. Now, we are extremizing, we are doing dt dx is equal to 0. We are trying to find out what is the extremum of that. We have found a condition. Okay. Now, what is that condition once again? We have just found the condition that n1 over c, remember n1 is the refractive index in medium 1. So, times x by root over h1 squared plus x squared, and that should be equal to n2 over c, root over n2 over c, and then L minus x root over h2 squared plus x squared. Okay. Now, what was the thing that we were doing? We were looking at refraction, okay, so from medium 1 to medium 2. Okay. Now, this angle was I, let us say that is the angle of incidence, and then this was height h1. So, this was x, so this was A, it is at B, and then the angle of refraction was r. Okay. So, this distance was h2, and so this was p and this was q. So, and OQ, this was L minus x, fine. Definitely this angle, that is angle OBQ, that is also r. Okay. Now, you have got a relation regarding some the refractive index times something, times x by something, some distance. Okay. So, let us find what that angle is. Oh, by the way, so this, if this angle is the angle of incidence, the angle PAO, okay, that angle is also I, right. So, in triangle APO, what do I have sin I to be? I have sin I to be x by the distance AO, which is nothing but root over h1 squared plus x squared, and in triangle BOQ, what is the sine of angle R? Well, sine of angle R nothing but L minus x divided by root over of h2 squared plus x squared. Therefore, when we come back to our old equation, which we have got by taking the time to be by making the time to be an extremum, okay, is if we substitute it back into our old equation, when over this equation here, this one, what we get is n1 sine of I is equal to this value n2 sine of r, okay, where I is the angle of incidence, that is the angle with which the light makes, or the ray of light makes with the normal when it strikes the boundary of these two media, and then r is the angle, that is the angle in which light emerges in medium 2. Okay. Now, this everybody knows as this as Snell's law in optics. Now, you see that we have simply obtained Snell's law in optics using Fermat's principle. Okay. And remember this mechanics problem I was telling you. So, if you wish to go from point A to point B, let us say, and then the region 1 was land and region 2 was water. Okay. So, what is the route you need to take? I mean, you better take the route AOB. Okay. That is also the thing you can work out using the principle of least action or in mechanics, right. So, to summarize what we have done today, so we have talked of the beginning of geometrical optics, we have talked of the fundamental guiding principle in geometrical optics, which is Fermat's principle, which actually tells you how the path of a ray of light. Okay. So, we have done that for reflection from a plane mirror, and we have also seen the path of light, the ray of light will take when it goes from one medium to another. Okay. And in doing so, what we have also found is that we are right, because we have reproduced the familiar laws of reflection and the familiar laws of refraction here. Fine, that is Snell's law. So, thank you very much.